Hi, folks. My name is Adil Latif. I'm a senior engineer working at Henrel, and I've been leading the Helix Plus capstone demo. We've had a very large team working on the capstone demo. If I go to the next slide, we've got folks from Henrel, PNNL, ENL, Lawrence Livermore, National Lab, all working on the capstone demo. Apart from this team, there were quite a few other folks trying to get this capstone demo going. Given that we were doing a multi-lab core simulation, we had requirements pertaining to uh, uh, for firewall issues and all of those. So we had a large team working on this, trying to get this core simulation done. What is this uh, capstone demo? When we were envisioning doing a capstone demo, what we essentially intended to do was highlight core capabilities of Helix in terms of complexity, in terms of its ability to be net vendor neutral, in terms of its capability to set up complex core simulations in a simplified manner. Then essentially also some of the cool features where you're able to do co-iteration on a subset of federates participating in a federation. Uh, to that end, what we essentially ended up doing was have a multi-domain core simulation. That is what we're going to showcase today. We've got a natural gas layer, and I'll talk about. We actually have two natural gas subsystems that I'll talk about later on. On top of the natural gas layer, we've got a transmission system that couples two that has multiple coupling points to the natural gas system, and then we've got a distribution system connecting to the transmission system. So we've got some rules of physics that need to be obeyed at those boundary conditions of T&D boundaries, right? And then we've got, I shouldn't say controls. I've got one controller, and the reason we use that one controller is to showcase some Helix capabilities that I'll talk about in the coming slides. All right. One thing I wanted to point out is that given we're doing this this capstone demo is a multi-lab effort, we've got folks that is spread out across of all of continental US. A lot of these folks are working on VPNs, which means that data gets routed to the national lab and then to the AWS server. So our main Helix broker, the server that is running that Helix broker is in AWS West 1, which is Northern California. And then we've got federates spread across all of US. So I just wanted to showcase the geographical locations and how efficiently we've been able to get this core simulation running, given the constraints on geographical locations as well. All right. So what is essentially the use case? We've got one transmission system. We've got three distribution systems. For the three distribution systems, we've got three different vendors for distribution systems. We've got two natural gas subsystems. And for both of them, we've got two different vendors for natural gas subsystems, both open, both closed source and in commercial tools. And then for one of the distribution system here, we've got a controller that is actually a volt file controller that is actually co-iterating with this distribution controller. The point I wanted to highlight here is this. Most of the federates here are loosely coupled, which means they're exchanging information once every time step and then moving forward in simulation time. These two subsystems are actually co-iterating, so they converge. They exchange information multiple times until convergence is reached. In this case, I just set it to 5 iterations, and then the maximum iteration limit is 5 iterations. And then once that convergence is reached, it asks for an increment in time. So essentially, within this use case, we've got a subsystem, a subset of federates that are loosely coupled, whereas a subset of federates that are tightly coupled. So that is one of the nice capabilities we wanted to showcase with Helix as well. All right, so what simulators are we using under the hood? For the transmission system, we've got MATPower. So we're interfacing, so it's working with MATLAB there. which is a commercial tool. We're using the Helix bindings for MATLAB there. For natural gas, we've got Saint, which is which implements a C# interface for Helix, and then it is a commercial tool, so you require a license for it. And the second subsystem for the natural gas that we're modeling, we're using NG Transient. It is natively written in Julia, but it interfaces with Helix using a Python RPC server. RPC server implemented in Python, I should say. And then this is closed source. For the distribution side, we've got three different distribution simulators. We've got PyDSS, which is a high-level interface to OpenDSS. It interfaces with the core simulation, the Helix binding in Python. We've got Eat and Sign, which is a commercial tool. We use the Python interface for that as well. And then we've got a third dummy distribution Federate, which is Python as well. And this is open source. And then we've got a controller, which is a volt-var controller, a simple algorithm that converges over a few iterations, and that is implemented in Python as well. The reason I put this here, I just wanted to showcase we're able to both interface with open source, closed source, and commercial tools. So essentially, we are vendor neutral. We support multiple programming languages, from MATLAB to C# to Julia to Python, right? Yeah. So what is essentially happening within the core simulation? So the Transmission Federate, what the responsibility of the Transmission Federate is to run the DC power flow every 1 minute, and the output of the natural gas federates is recorded once every power flow, so essentially every minute. Every 5 minutes, so every fifth time point, we run a DC power flow, which creates a difference between the generation pattern, right? We do have variability within the loads as well, where bus 4, for example, the ramps linearly from 65 megawatts at 3600 seconds and then back to 47 megawatts, right? What I show in this graph here is, what the transmission essentially is doing with the natural gas is actually asking for a particular. We've got natural gas generators on the natural gas federates. The transmission federates request for a certain amount of megawatts. If the supply is sufficient, the natural gas federates would be able to supply it. Else, you would see a curtailed value. Unfortunately, we don't see that curtailment here. We were hoping to get those in some results that were a bit more interesting. But what you see here is that what was asked for by the OPF is what you get from both NG Transient and Saint simulators. All right. I just wanted to highlight a few pieces here as well. So what is happening is essentially within the natural gas federates, you've got so the transmission is requesting a certain amount of natural gas, a certain amount of power, right? The request may or may not be available given whatever the constraints are within the natural gas model, right? So the delivery is computed by NG Transient, and something similar is done within the Saint model as well. If the request cannot be met, what essentially is going to happen is that the natural gas-fired power plants are going to be operating at a suboptimal dispatch level, and you would see that that what is requested is not what is granted. In this case, however, given we did not hit that constraint limit, we were able to match what was asked for every single point in time in the core simulation. All right. The same is true for the second natural gas federate as well. Here we see some flows within the natural gas. I am not the domain expert within the natural gas. So if you have any questions, I think we do have Brian that can talk to these results. But essentially, the overall concept is exactly the same. In this case, the only difference I believe is that the natural gas federate for Saint is updated every 15 minutes compared to 5 minutes for some of the other simulators. All right. And then for the distribution federates, So state variables are exchanged at the T and D boundary. So we've got voltage coming in from the transmission side, and P and Q is dispatched from the distribution side. We've got three distribution federates. I've talked about this already. We've got SIME, OpenDSS, and a Python federate that are coupled to three different transmission nodes. Given we are running DC power flow, the transmission side, the voltage magnitude is unity on the distribution side, which is why I did not plot voltage because it wasn't very interesting. And then all right. So another piece I wanted to highlight here was that the one difference between the distribution federate and the controller is that unlike all the other components or all the other federates, these are tightly coupled. So the controller is tightly coupled to one distribution federate, in this case, the OpenDSS distribution federate, and we do see convergence being reached in about 3 to 4 iterations. All right. Concluding, the capstone demo was designed to showcase the capabilities of Helix in terms of operability, in terms of simulation scaling. We can be geographically in very different locations. We're still able to get the core simulations running in somewhat smooth manner. We wanted to showcase this co-convergence capability, so you don't have to have the entire federation running in co-iteration, which would significantly increase the core simulation time. But compute time. But essentially, what you can do, which I think is a very nice capability to have, is have a subset of federates running in co-iteration. And we also wanted to showcase usability. We're able to interface with most existing open source and commercial tools, and get them to work within the core simulation framework. And with that, I'm ready for your questions. Thank you.
Awesome. Thanks so much, Otto. This is a lot of great work that you helped lead, and certainly with the full team of folks you highlighted earlier. Just as a heads up, we have a little bit of a NC handoff here. Jason had to drop off, and I was running a little bit late, so I'll take over from here. But we've got about 10 minutes or so for questions, and it seemed like a lot of great work here, so I'm hoping they'll have some good conversations. Go ahead, Abhijit. You see your hand up, but it looks like you might still be on mute if you're asking a question.
Sorry. Yep. Hi, Adil. Yeah, nice talk. And I wanted to understand this concept, like you have a tightly coupled system and loosely coupled system. So you mentioned that your controller for volt-var control, it is running. So I'm just trying to understand the time resolution with which the controller take decision. Is it dependent on the distribution system that is tightly coupled or loosely coupled? How is it like?
So in Helix, there's the mode called request iteration if needed, right? So essentially, what we can do is we can ask for a federate to iterate only if it is required.
Oh.
Does that make sense?
Okay.
So if there is a federation, if there is a federate that is requiring iteration, we can try and get that done. So and that would require more than one federate to have that capability enabled, right? So when we're requesting time, instead of moving forward in time, I'm requesting the same time, but I'm requesting to iterate. So we're able to iterate for a subset of systems.
Okay. So how about this controller? The controller would be running with what kind of time resolution? Like
the same time resolution, so the same time step, 1 minute resolution.
Okay.
But it has the added ability to iterate, right? So it's going to be moving forward in time at 1 minute time step. So exchanging information multiple times each simulation time, essentially.
Okay. Okay. Thank you.
Yeah. So we're not like dilating time and trying to do it that way.
Okay.
Yeah. The simulation time stops there until we reach convergence, and then we move forward.
Yeah, I thought it because, like for one distribution system, you are waiting until the convergence takes place, right? So it's not a single snapshot, it is a multiple sequence of snapshot coming along, right?
Th-
And that is also independent of scenario when the number of iteration may vary, right?
That
Um,
is, yeah, that is correct. So what I haven't tried is like really have like two subsystems iterating independently and see what happens if things
okay,
break or not.
okay,
So
okay.
that is something, yeah, I've never thought about.
Very cool. Seems like you got another question from Anish.
Yeah, hi Adil. Thanks a lot for the presentation. This capability looks really cool in terms of running different simulators from different locations. I just wanted to sort of uh, hear from you about your experience in terms of what are some of the bottlenecks or lesson learned by trying to get all of these federates in different locations to work together. In terms of if someone wants to do this in future, what should they sort of learn from this experience and keep in mind so that the process becomes a little more easier for someone in future?
Yeah, so what Karthik did suggest, and I think I am going to do that once I get a time, is have a shared wiki for this experience. Just because it wasn't very straightforward early on. Once we figure out all the intricacies of Helix and all of those pieces, running the core simulation becomes very easy towards the end of this effort, right? But early on, we ran into a lot of issues uh, with uh, not only with like the firewall, but also how we were actually setting up the core simulation. So lessons learned definitely need to be shared and I mean shared with the larger audience, and we will work on a wiki to be able to share that in a nice manner. I would say latency did not seem to be an issue. We had only one issue, I think, one instance where a connection timed out. Uh, Debugging becomes a little bit challenging because as soon as you start to so if one person is actually running Python in, let's say, debug mode, you would cause the core simulation to crash at that point as soon as you enter into debug mode, just because communications time out. So we've got so there were these issues with the debugging pieces and all of those pieces that I think we need to think about more, and how to actually help a larger core simulation when we have these requirements of being able to debug and pause things and all of that. Uh, but yeah, overall, the way we approach this was first start with dummy federates. So things that do very minimal things, make sure that the communication is working, and then actually introduce the real simulators and see if you're able to get the same thing to work again. That kind of helped uh, with the transition to actual simulators. But even then, there are, I think, things we still need to think about as we move forward with large scale, like multi location core simulations.
Just a
Thanks.
note on the debugging stuff. There is a debug flag which turns off all the timeouts that you probably would have been helpful for you to know about.
Okay, sorry, sorry about that.
Thanks, Phil. Hey, there's lots of great features like that. So maybe we can include that as part of our. I love this idea of the sort of lessons learned wiki, and putting in hey, we ran into challenges with this. Oh, but look, now we know for the future to turn this switch on, and hopefully that'll work better. That's
Yeah,
cool.
and if there are other suggestions you come up with that we could implement in Helix, let us know.
Yeah, and
Very
there
cool.
are other intricacies as well. So, for example, if you want the broker to pause until all core simulations start up, how do you do that? I think that is a good lesson learned as well. We can talk about all of those pieces within the wiki space.
Sounds great. Looks like there's another question from Trevor.
Yeah, actually, related to the kind of the debugging aspect is how much did the standardized interfaces we've been working on help, and how much was that just like one piece, and there's actually 3 or 4 other things you also have to do to make this like really easy to, or maybe easier to do?
So Trevor, I don't think we had any issues with the interfaces, truthfully. Yeah, one thing I did wanted to highlight, and thank you for that, Trevor. So we do have standardized interfaces for the natural gas federates, and even for the distribution, the SIME and the Open DSS. I think I've highlighted in the first presentation that we did. They've got common interface, a standardized interface, which means you can actually switch between them, and the user wouldn't even know what simulator you're using under the hood. So we did not have a single issue with the setting up of the core simulation, but it was just running of the core simulation, trying to synchronize. So essentially, when we're starting up all our federates, we want to make sure that the core simulation doesn't start on that end. So that was a little bit challenging, but the interfaces were very stable.
Yeah, that's interesting to hear. Yeah, obviously, I'm glad that the interface part, which we knew would be a challenge, ended up not being a challenge because of the work we'd put in. But yeah, to realize there's still like 3 or 4 other challenges here that it took this demonstration to kind of realize. I'm glad we've done it then.
Yeah, for sure. I had a sort of follow-on question to that, which was, I remember early on there were some issues with sort of everybody agreeing to the same time steps and things like that. I was curious if there's other kind of fairly simple nuggets like that are up for sharing, or maybe experiences in there, like maybe that's something we need to specify in other ways, or where the dummy federates may be capturing that or not. Just like if there's thinking about other kind of concerns like that.
So one of the issues was that when we were doing the initial simulation, our time steps did not match because we've got very different simulation tools, right? We don't have a shared Helix implementation, which means we want to synchronize all of that. If we have a config file that is able to I don't know how if like multi-site core simulation becomes tricky because you don't have a shared config file, right? So everything needs to be not in step, but essentially the configs need to be the same. The simulation time need to be the same. Simulators can be running at different time steps. I believe we have simulators in this core simulation that weren't actually running at the same time step. So some of them were 1 minute, some of them were 5 minutes, and then we've got one that is at 15 minutes as well, I believe. So that is, Helix is able to handle all of that. That's not an issue. But having a shared config file, because in our case, certain simulators were running for a day, some of them running for 2 hours, some of them. So we had to, that it took us quite some while to figure out, to get things right in that aspect.
Yeah, it makes sense. And it seemed like some of those are nuances that you may not capture with the dummy federates, because the dummy federates are simple enough that you get the data exchanges right, but perhaps not the how long is it going to last and some of those other pieces quite the same.
Yeah, I mean, for that you would have to have like a shared config file, right? That everybody's able to ingest and then make use of somehow. I don't know.
Very cool. Well, we're getting towards the end of time. If there's any last burning questions, we can quickly answer them. Otherwise, I want to talk through the last little bit of our seminar series too. Any last questions for Adil and the team? Well, all right. Well, we'll take that as a no, and just wanted to thank everybody again for joining this week. And we do have one more week left in this series. It looks like I'm probably sharing the non-pretty view. Let me see if I can fix that. Here we go. We're here at the session 5. Thanks again to Anandeep, Manish, Jacob, Adil. And we're moving into next week, and we'll have our last sort of technical presentation from Trevor on the standard interfaces we were just discussing a little bit about. And then the sort of second half of next week, we're looking to have a bit more of a discussion to think about our future directions for Helix as a tool, and potential use cases and partnerships, and what does it look like to further build the community around Helix, and consider commercialization pathways in that area too. So please bring your ideas to that. We're hoping that'll be a true and lively discussion. And for next week, that will be our last one after that too. These are available through YouTube and the recordings of most of them as we go forward. So thanks, Trevor, for putting those up. And thanks everybody else, or everybody who's been a part of the series so far, and looking forward to catching everybody next week. Have a good one.